Now, if we go back to that question, how long did it take for me to bike from home to Illinois during August 2018? At first, my answer was around 21.31 minutes. Now, given that I learned that reporting on the standard deviation is a good practice, I have improved, let's say, this answer by saying around 28.31 minutes, give or take 1.7 minutes. Now you may be asking yourself, well, why 1.7 minutes if when we look at the sigma was actually 0.86, right? And 1.7 is actually 2 times the sigma, 2 times the standard deviation. Why? Why did I choose to report on 2 times the standard deviation and not just 1? There's actually a very interesting reason behind that. And that is because of how the normal distribution is shaped and how all the things that we know about normal distributions. One thing that is cool about visualizing your distribution and then realizing that it follows a certain pattern, that it follows a certain shape that you know, that you've seen it before, and that you've seen it happen in other data sets that is not your data set. The interesting thing is that we learn how to interpret these shapes. So when a new data set comes and it has the same shape or roughly a similar shape, then we can actually make assumptions about that data set based on what we know from previous data sets that have the same shape, right? So for example, the normal distribution is, I guess, I think I would not be saying anything wrong if I said that the normal distribution is probably the most well-known distribution shape. And it's actually one of the most common ones. It happens everywhere in real life when we measure things in general. Actually, I have a link here with examples that we can look at. Yeah, so I guess that you're seeing the same thing that you're seeing, hopefully. Examples of normal distribution and probability in everyday life. So you can see that in this website, there's a lot of data that actually follows the normal distribution, and it looks, I mean, at least when I saw it for the first time, I was amazed that so many different things from real life can have the same shape when you measure data about them. So for example, well, this is one very simple, very common example, which is the probability of heads. This is a simulation of the probability you would get heads on a coin toss from 1 coin toss to 100. So if you took 100 coin toss, or in this case here, in this case it's 16 coin tosses. So if you take 16 coin tosses, you just throw a coin 16 times, then there are different probabilities for how many heads you will get in these 16 coin tosses, right? So for example, there's a very low probability that you will not get any heads, so it's 0. 0 is very low. Then there is like, okay, what's the probability of getting 4 heads in 16 coin tosses? Well, it's about like a little bit less than 5%, which is also very small, like 5% very small, because it's 4, right? 4 of 16. Well, it's small. What's the probability of actually having 7 heads in 16 coin tosses? It's actually around less than 20%. And then the largest one is, of course, 8, and that's simply because there are only 2 probabilities, heads or tails, and you're throwing it 16 times, so it's expected, so to speak, that you get 8 heads and 8 tails in general. You will not always get that, but in general, since it's 50-50, then the largest probability is this one. But it's still like around 20%, right? So it's not that much, because there's a lot of other possibilities also. So it's more than the others, but it's still not 50%. It's a very classical example, but for example, this is another one that's very interesting, which is a histogram of the birth weight of newborn babies. So it goes all the way from around 1 kilogram, large, actually goes to 400. Okay. Let's see better now. So, for example, the birth rate goes all the way from around 1 kilo to around 5 kilos. And that's very interesting because it's a good example of the stuff that we saw in this previous slides, which is, well, these are the measurements of 3,226 newborn babies, right? It's from a paper from 2002. The mean is 3.39 kilos, and the standard deviation is 0.55 kilograms. So you can see that actually standard deviation is not that big, right? The data doesn't vary that much. On average, the values are 550 grams away from the mean. Of course, there are outliers that are very small. Of course, there are outliers that are very large or very heavy. But in general, you can expect babies to be between, let's say, 2 kilos and 800 grams to 3 kilos, 900 grams, or something like this, or 4 kilos. More or less, on average, because the standard deviation tells you that it kind of varies a little bit from 500 less than the mean and 500 more than. Now, if you plot the data, then you can see that it's, again, of course, it's not perfectly normal. Of course, sometimes the normals are a little bit thinner, sometimes they're a little bit wider, but still, it's a normal distribution. It's very much like a normal distribution. You can see that it starts very small, then it shoots up very quickly, then it goes down again very quickly, and after a while, you don't see much better. Now, the reason why I came to this was because I wanted to show you that I wanted to explain why is it that I was talking about 2 standard deviations and not just one. The reason is that by looking at so many different normal distributions in real life, people realize by measuring the normal distribution or measuring the data that actually results in normal distributions, that around 68% of the data is within 1 standard deviation of the mean, plus or minus. So that's what you see over here in this graph. You have the mean here, but then you have 34% to one side, 34% to the other side. So if you take plus or minus 1 sigma or 1 standard deviation, you have 68% of the data is in that region. If you extend 1 more standard deviation, so you take 2 standard deviations minus or 2 standard deviations plus of the mean, then you actually get 95% of your data. So you see, I mean, 68% is good, but 95% is much more confident, right? So if you do it again and you expand 1 more standard deviation minus or plus, then you get actually 99.77% of the data points. So there's very little. Anything that falls more than 3 standard deviations to the left of the mean or more than 3 standard deviations to the right of the mean, you can consider them as being outliers. They are not representative of your data. They are just very unique data points. And their influence in how you understand your data should not be very strong because they're outliers. Maybe you've got an error in your measurement. Maybe you measured something wrong. Maybe there was an atypical some kind of a weird event that happened during a data gathering, so it generated an outlier. And these data points that are too far away from the mean in a normal distribution, they shouldn't really take that much seriously, so to speak. This is known as the empirical rule. So whenever you hear about the empirical rule, it's basically the rule that tells you how many or how much percent of the data is within a specific number of standard deviations away from me. And that's why I decided to reply on give or take 1.7 minutes, because this is 2 times sigma. So since my distribution here looks roughly normal, right? It's not perfectly normal, but it looks roughly normal. Then I'm confident in saying, well, 95% of my data points are within -2 or +2 sigma from the mean. And -2 and +2 is basically -1.7 or +1.7. So I could say that somewhere around 20, like 6.5 to 29 to 30 minutes, or something around 30 minutes, right? And that's why I decided to reply it like this. Just one quick clarification. The empirical rule only works for normal distributions. You cannot just take any distribution and say, yeah, there are 95% of the data is within 2 sigma of the mean plus or minus. No, that is only for the normal distribution. So since we know so much about the normal distributions, so we've seen it before so many times, we can assume that. But if it's not normal, then you can't really assume.